Hi everyone, this is week 9 and this week we are starting a new chapter, the chapter called integration. And in this first section, we will talk about estimating rectangles, how we estimate area under curves by using rectangles, and then I will talk about Riemann sums, then we talk about sigma notation, and at the end, at the last part, I will try to explain the relation between area under curves and the definite integral and how we use the geometric meaning of definite integral to compute it. Is my voice clear now? I guess it's better now, right? Okay, so if you hear me clearly, we can continue with this first example here. What do you want to find? Let's see. We want to find the average value of f by using an approximation to the area under the curve. So use a finite sum to estimate the average value over the given interval by partitioning it into 4 sub-intervals. These are the important parts of the example. Let me first divide the given interval into 4 sub-intervals like that. You see, I divided the interval from 0 to 4 into 4 sub-intervals like this. And there is also another detail in the statement. It says use midpoints. How do we use midpoints to construct our estimating rectangles? First of all, let's mark the midpoints like this. These are the midpoints of the given interval. This is 1/2, right? This is 3/2, 5/2, 7/2. Now, I am constructing the approximating rectangles by using midpoints. I start with the midpoint, go up till the curve. When I hit the curve, I stop. This will be the height. This part will be the height of my rectangle now, and I will complete the rectangle over the given base like this. Let's do it again. By using the midpoint, I go up till the curve, which will give me the height. This will be the height of the second rectangle. And then over the given interval, you can easily complete drawing your rectangle like this. Do the same for the next. This is the midpoint. I go up till the curve, and then I complete the rectangle over the given base. And the last midpoint, last approximating rectangle. Why we draw 4 rectangles here? Because we are trying to estimate the area under the curve, which is the same as the definite integral. Okay, so let me write the relation now for you. We are trying to compute f average, where f is given by this expression. And there is a formula for it. We covered this formula in the lecture videos. It is like that. You first need to compute this definite integral, and you should divide it by the length of the interval, okay? We know what is a, what is b. They are given here. The interval is given. Okay, let's write this down. So it is from 0 to 4. What is the function? Function is given like that. Cosine pi t over 4 to the power 4. Now, length of the interval is 4 minus 0, of course. Okay. Now, I want to give an estimation for this average value. The question is not finding the exact average value, but it says give an estimation for the average value by giving an estimation for the definite integral. Estimation for definite integral, let's say. Okay, let's name it as area estimated. I use this notation AE because I will compute an estimation for the area under the curve. Area under the curve is the same as the definite integral. Okay, so what we need to find now is this estimation for the area under the curve, and it will be done by using this approximating rectangles that we draw here. We draw 4 rectangles, and we will find the sum of the areas of these four rectangles to get an estimation for the exact area under the curve, which is the same as the definite integral. Okay, so let's do that. So sum of the areas of four rectangles that we draw there. Okay, let's say A1, A2, we have four rectangles, A3, A4. And if I find this sum, it will give us an estimation for the exact area under the curve, right? Okay, let me write it like this again. From 0 to 4, we have f of x dx in the formula. And this definite integral is approximated by the sum of the areas of the rectangles. And that's what we are doing now. Okay, so what is A1? A1 is base times the height. You know, I already mentioned that. Okay, this is the height of the first rectangle, and it is given by the function evaluated at the midpoint. And similarly, this is the height of the second rectangle, and it is given by the value of the function evaluated at the second midpoint. So let's write them down. And the second area of the second rectangle is given by base times height, 3 over 2. Similarly, 1 times 5 over 2 is the height, 1 is the base, 7 over 2 is the height of the last rectangle. Okay, let's find out the result now. So these values of the function can easily be computed because the expression for the function is given like that. 1 minus cosine of something to the power 4. So it goes like 1 minus cosine. You will insert 1 over 2 for t. You see, you have t here, and you are evaluating at 1 over 4 for the first rectangle. So if t is 1 over 4, you have pi over 8 there, right, in the function. So let me write this down. Pi over 8 to the power 4. This is the image of function. Okay, similarly, it is 1 minus cosine. Again, insert 3 over 2 for t there, so you will obtain this. And I keep computing the image for each rectangle. Now I will insert 5 over 2 for t. That's why it is cosine 5 pi over 8 to the power 4. And this is for the last one. Cosine 7 pi over 8 to the power 4. And this is the value of f evaluated at pi over 2 and sorry, 5 over 2, and the last one is the image of f evaluated at 7 over 2. Okay, if you compute this thing, you will find the average value, and this I denoted by area estimated, right? That's why now I will just, I won't compute this whole thing. You can use your calculators to do that. But what you should do is find out the result and put it here in your formula. Then that will give you the average value for you. Okay, I will leave the solution like that. I hope you got the idea. The idea here is the definite integral, this part, is estimated by the sum of the areas of the rectangles. Okay, this definite integral can be estimated by using approximating rectangles like this, and we use 4 approximating rectangles here. Obviously, the sum of the areas of those 4 rectangles does not give us the exact area under the curve, right? For example, let's see the error. This is the error. We have errors. The sum of those 4 rectangles is not the exact area under the curve, but approximately. That's why we put here the approximating sign, not exactly equal sign. Okay. So if no questions about this part, I will continue with the next example. Okay, next two examples are related. Don't read this statement, I will summarize it for you. 21 is the particular case of the example given in 22. So this is the general case. If we can solve 22, you can easily apply what you find for the particular case to compute 21. So let's deal with the difficult case, the general case. Let's try to understand the statement now. It says inscribe means put inside an n-sided polygon inside a circle of radius 1. Okay, we want to inscribe an n-sided polygon inside a circle of radius 1, and then we will compute the area of one of the n-congruent triangles that forms this n-sided polygon. So this is the question for part A. Let me insert here a very nice circle of radius 1. But wait, color. Okay, I think this one is a nice circle of radius 1. Now what will I do? I will try to inscribe an n-sided polygon inside this circle. How can I do that? Okay, let's mark the center like that. Now this is a circle of radius 1. You can divide this circle into n parts to inscribe an n-sided polygon inside it like this. You see, if I connect these points, vertices, you start forming your n-sided polygon, right? That's what they meant by inscribing an n-sided polygon inside a circle of radius 1. So you keep drawing these rectangles till you reach n-sided polygon. So you need to draw n many. It will continue like this. Of course, I cannot draw all of them. But what we know here is there are n many triangles here to form an n-sided polygon, right? Okay, the question was, find the area of one of these congruent rectangles. Let's concentrate on one of them. So let's concentrate on this triangle. And our aim is to compute the area of it. By using the area of one rectangle and then multiplying by it n, we will find the area of this n-sided polygon. First of all, to find out this area of the rectangle, of the triangle that I shaded in yellow, we need to understand this angle. In total, we have 2 pi measure, right? We divide this total count here into how many parts, how many triangles, and many. That's why this angle here should be 2 pi divided by n. Okay, because we divide into n many triangles. Let's take this triangle here, concentrate on it in a more detailed way. Okay, I computed this angle as 2 pi over n. Now I am interested in the area of this triangle. Our aim is to find the area of it. Okay, the total measure was 2 pi over n. I divided it into 2 parts. That's why divided by 2 pi over n and pi over n it should be. And then of course these two lengths are equal. The sides are 1 because it was a circle of radius 1, and this is a right triangle. Now, concentrate on this triangle to find the area of it. I will use some trigonometric information here to find the values for A and B. What is A and what is B? I need to find these lengths to find the area of this triangle. Can you tell me the sine measure of pi over n? So just concentrate over here, for example. What is sine pi over n? You can easily use this right triangle to find out this value. What is it? Opposite edge divided by hypotenuse, right? A over 1. So A is given exactly as sine pi over n. Similarly, what is cosine pi over n? This time it is adjacent edge divided by hypotenuse. So you see, you computed cosine like that, cosine pi over n. Sorry, you computed the value of b like this. Okay, we have A, we have B. That's why we can easily compute the area of this triangle now. Area of the triangle is given as base times height divided by 2. So it is A times B. A is sine pi over n times B, sine pi over n. This is A, this is B. This was easy, right? Not that difficult. We find an expression for the area of the triangle. Now we can find an expression for the area of n-gon, n-sided polygon. I just need to multiply this area of the triangle by n. Area of n-gon. Let's say it should be the n times area of triangle. Okay, so n times sine pi over n times cosine pi over n. Okay, this is the expression for the area of n-sided polygon. Why did I compute it? Now I will relate this discussion with the geometric discussion that we had for the definite integral. Let's try to construct a relation now. What if, by the way, let me write this as a more simple form. You know, this part can be re-expressed as sine of 2 times that angle, right? What I mean is, this is in fact sine of I double the angle. Sorry, you see I put this coefficient 2 here, but then I need to divide by 2. You remember half angle formula, right? Let me remind it here. Recall, sine 2x is 2 times sine x cosine x. This is the formula. You see I have sine x cosine x part here. It should be sine 2x divided by 2. That's what I did here. That's why this result is sine 2 pi n over 2. Okay, this is the formula expression for the area of n-gon. Now, can we relate this area of n-gon with the area of the whole circle? You know, the area of n-gon and the area of the circle are not the same because of these error parts, obviously. So the area of the polygon is very close to the area of the circle, but they are not the same because we have these errors here. How can I get rid of these errors? By increasing the number of triangles, I can decrease the amount of error, right? The more triangles we have, the less error we obtain. That's why now there is a passage from the area of polygon to the area of the circle. How can I relate these two? Area of the circle. How can I relate them together? Area of n-gon. Obviously, they are not the same because of those errors. If I send the number of rectangles to infinity, can you try to imagine what happens? If you insert infinitely many triangles there, you would get rid of all the error, all the red parts there, okay? Maybe I shouldn't do that blue part. Okay, let me emphasize again. If you send the number of rectangles, this will only then you can get rid of the error in the area. So you know these blue parts are the difference between the area of the polygon and the area of the circle. But there is a way to get rid of those error parts. If you send the number of triangles to infinity, then the area of the n-gon and the area of the circle would be the same. Okay, this is the only way. So the relation is like that. If you send the number of sides of n-gun to infinity, then the resulting area should be the same as the area of the circle. That's our expectation. Let's see if they are the same. Now I will compute the limit. Area of n-gun, the expression for that is computed above. We computed that expression as 2 pi over 2n. So this expression, okay? Wait, it is not 2n. There is n here, n times this. Okay, so how can we compute this limit? There is another recall here that I can remind you. Do you remember this useful formula? What was this limit? We covered this in the beginning of the semester. It was 1. And now we can use this here. Normally, if n goes to infinity, this part goes to infinity, and sine 2 pi over n. Sorry, I forgot to write something here. You should warn me about those mistakes. Okay, this was the angle. Sine 2 pi over n as n goes to infinity goes to 0. That's why this part, sine 0 is 0. So it is in this form is an indeterminate form. So we need to invent something to get rid of this indeterminate form. And you can do it like that. Limit n goes to infinity is there. You can take that n coefficient to the denominator, see, and then see what happens. 2 over n. I will just write n to the denominator as 1 over n. And then, you see, if I also multiply with pi, the angle here and here would be the same. And as desired, as n goes to infinity, this angle expression goes to 0. So it is exactly in this form. So that, by the way, since I multiply denominator with pi, I also multiply denominator with pi, not to change the question. So now I am ready. This part goes to, what is the limit of this part by using that rule? It is exactly of that form, so it goes to 1. So the result of this limit is just pi, comes from here. Okay, let's compare this result with the area of the circle. What is the area of the circle of radius 1? Pi r square, right? Where r is 1, radius is 1. You see, everything makes sense. We find the same result as we expected. So you should just compare the result. They are the same as we expect. So if you send the number of rectangles to infinity, then your n-gun becomes exactly like the circle, so that you don't have any differences between those areas. If n goes to infinity, your n-gun behaves like the circle. So their areas becomes the same, only in the case when n goes to infinity. And this idea is what we use. Why I explained this example to you? Because that's the idea, sorry, that we use. Just a second, let me invent some. Oh. Okay, let me put some space here. And I will explain this one goes to 1. Okay, why I explained this solution, this kind of exercise to you? Because I want you to see the similarity, let me call it as recall. Similarity between what we are doing with the curves to estimate the area under them. Okay, this is what I explained in my lecture video. Let's say you have a function over this interval AB and you are trying to find area under it. This is so related to the definite integral. In fact, this definite integral has a geometric meaning. It is the same as the area under the curve. And what we do to estimate the area under the curve, we divide the interval into subintervals, just like we divide the circle here into n many triangles. Just like that, we divide the area under the curve here into n many rectangles. Instead of triangles, we are using rectangles in our usual case. So after finding find the sum of the rectangles, sum of the area of rectangles, and we will be using sigma notation for them. Sigma notation. Let me choose AK. This is the area of kth rectangle. Okay, so this is a notation for the sum, writing the sum of them. So we have n many rectangles, and this is the sum of the areas of them. And right now, they are not the same. They are approximately the same. This definite integral means area under the curve. Okay, if I put n many rectangles there, I know the area under the curve is not the same as the sum of the areas of those rectangles, because you know there will be errors, like I highlighted as yellow there. How can I get rid of those error parts? By putting, or in other words, how can I make this approximately equal sign to exactly equal sign? Of course, by sending the number of rectangles. What happened? Şimdi, can you see me in Zoom meeting? Okay, sorry, I just thought that I lost my connection, but we don't. Okay, so I was just saying that if you send the number of rectangles to infinity, only then you can put equality sign here. Area under the curve is the same as the definite integral, and it is the same as the sum of the areas of all those rectangles when the number of rectangles is sent to infinity. Okay, so I think now you can see the similarity. Here we were trying to approximate the area of the circles by using infinitely many triangles. Here, and as usual throughout this chapter, we will be using rectangles to approximate the areas under the curves. The more rectangles you have, the less error you obtain, which means if you have infinitely many rectangles, you will find the exact area under the curve. That's the idea. And the right-hand side that I put here is called as the Riemann sum. Okay, so that's the similarity. Any questions now? I think this exercise is important to understand the relation between the definite integral and the area under it, and how we use approximating rectangles or triangles to reach the whole picture. All you need to do is to send the number of your triangles or rectangles, whatever you use, to infinity. Only then you can get rid of the errors. Okay, that's all for that. If no questions, let's continue with the next exercise, which is about sigma notation. Let me put here a very quick recall about sigma notation. This is the sigma notation, and here AK means something depends on K. For example, 1 over K, or any expression depending on K. What does this notation mean? It means that you put K equals 1, K equals 2, K equals 3, all the way up to N. So sigma notation basically means a summation, a finite summation like that. Okay, now let's solve some exercises by using sigma notation. 26. K runs from 1 to 7. K times 2K plus 1. Okay, let's first do this product to see what we have. 2k squared plus k. Okay. First property of sigma notation. You can distribute sigma notation over sum. So you can write this as 2k squared plus sigma k from 1 to 7k. You see, I distributed over sum. This is a property of sigma notation. Another property is that you can take all the constants out from the sigma notation. Everything that doesn't depend on k can be taken out from sigma notation like this. So 2 times 2 goes out, and your sigma notation is like that. And after this point, we need to use some formulas that I gave in the lecture video. Sum of numbers, sum of squares, and sum of cubes. These are the formulas that you need to remember. Maybe I can put another recall for that for you. Okay, another recall. Sum of numbers from 1 to n, there is a formula for it. It is n plus 1 over 2. Now, sum of squares from 1 to n, the formula for it goes like n plus 1 to n plus 1 over 6. And maybe we can also put here sum of the cubes from 1 to n. And its formula is n plus 1 over 6 squared. We mentioned all of those formulas in the lecture video. Now it is time to use them. So this is sum of squares. And what is n here? N is 7. Look at your formula. It goes like that depending on n. So for this one, I will write n plus 1, 8, 2n plus 1, 15, divided by 6. And the second expression is sum of numbers from 1 to 7. It goes like n plus 1, 8, divided by 2. Okay, so your result looks like this, which is, I guess, if you compute it, you will find 280 plus 28, 308. Okay, this will be your result. Okay, this is how you play with sigma notation. And let's solve 29 now. Part C. Okay. It is a funny exercise. Sigma notation from 3 to 264. And inside it, they put 10. And as you noticed, 10 doesn't depend on k, right? So let's try to understand what's happening here. I write 10 for k equals 3, right? Another 10, another 10. For each k, you keep writing 10. This is for k equals 3, k equals 4, k equals 5, and it continues like this up till for k equals 264. You see, I write 10 over and over again. To find the result, I need to understand the number of terms here. How many 10s I wrote here? That's the question. So what is the number of terms? Number of terms, you can compute it easily by 264 minus 3. Not to lose the first term, you need to add plus 1. So this is the number of terms. So that number is 262. So number of terms times the term. I'm times the value, which is 10. So your result is 2,620. Okay, like that. If you have constant expression in your sigma notation, what you should do is to multiply the value, which is 10, with the number of terms. And in general, we put a rule for it in our lecture notes. So the item for this kind of exercises in our lecture notes was k is from 1 to n. If you have something like this where c is a constant, then the result is number of terms sorry, not K, but N, you will put C, N many C's there, number of terms, N times your value. Okay. Next, let's try, for example, okay, 32. Part A. Again, very similar. 1 to N, 1 plus N to N. What is happening here? You should first notice that this is just a constant with respect to K, right? Because it doesn't depend on K. It is just N, constant. So I keep writing this constant over and over again. Very similarly to the previous example. This is a constant. I keep writing it for K equals 1, for K equals 2. And the last term is for K equals N. You see, N is the last term. So the result of this finite sum is number of terms times the value. So number of terms is obviously N this time times the given constant there. So the result is 1 plus 2n squared for this case. Okay. And before the break, I think we can solve part C of 32, which is this one. It is K is from 1 to N, K over N squared. So what do we have here? 1 over N squared. This is just a constant that doesn't depend on K, right? So you can just take it out. And then what is left inside is just K, where K runs from 1 to N. So you know, we have a formula for sum of numbers. This part has a formula, n plus 1 divided by 2. So the result is n plus 1 over 2n, I think. Like that. Okay? So that's it. Any questions about sigma notation? I think together with the ones we did in the lecture video, this is enough about sigma notation. So let's move. Any question about that? Any question about sigma notation? You deal with it like this. Okay, the next group of questions is about Riemann sum, which is a very important topic. And I think I should stop here. I will start doing that after the break. Okay, let's take 10 minutes break here.